Good morning, good afternoon, dear students. Today we will be talking about epilepsy and seizures and the role of the EEG in epilepsy. It will really be an introduction, so I will be scratching the surface to some extent, but it serves as an introductory part of the course of epilepsy. And as I assume that most of you are not familiar with epilepsy at this moment, I decided to discuss it initially at a relatively simple way, but to introduce some general concepts so that you get a little bit of a feel and a flavor of this particular neurological condition. So let's start immediately with a typical seizure that we can observe in our patients. And that's shown in this slide. This is a patient. He is being monitored in an epilepsy monitoring unit. So he has electrodes attached to the scalp, and he's reading a newspaper, and this is part of the EEG at this moment. Now, you're not experts in EEG yet, but there are some patterns I think that you can recognize. For instance, this is the EKG, the electrocardiogram. This is some muscle activity, and shown otherwise are the various rhythms of the brain recorded from several locations. And generally, those rhythms are in the 0.5 up to, say, 35 hertz frequency range. There are much higher frequencies in the brain, and in part they can be recorded at the scalp in slower frequencies, but for now this suffices. Now let's have a look what happens to the patient while he is reading. So nothing really going on yet, except for now. So very suddenly there is a loss of consciousness and a bilateral, generalized tonic contraction of the muscles of the arms, the neck, and the legs. And now the clonic phase starts, the rhythmic jerks, and this typically continues for 1 minute or a few minutes. And clearly the EEG is hardly interpretable anymore because there are so many muscle artifacts. In this particular patient, this episode was about 2 to 3 minutes, I think. And then, fortunately, most seizures end spontaneously, and this is slightly after the end of the seizure. You can see that the EEG has slowed. It's much more slowing now, which is not completely trivial to explain, by the way. And the patient obviously doesn't feel very well. We call this the postictal state. A lot of patients complain of headaches. They can be confused. They oftentimes have partial neurological deficits that tend to completely recover. And this particular state can last for minutes, but sometimes hours and sometimes even days. So it's not only the seizure, but also the postictal state that is definitely not very pleasant for the patient to experience. So what have we observed? This is an example of a primary generalized seizure. What is a seizure in general? Well, you can define a seizure as a sudden change in behavior, perception, or consciousness. It can be all of the three, resulting from abnormal synchrony of neural networks. And the cortex is actually always involved, the cerebral cortex, in a seizure. In a cartoon, you could display it in the following way, because some seizures, the seizures you just saw was a primarily generalized seizure. The patient was suddenly unconscious, and there were tonic and later clonic muscle movements from both extremities at the same moment. Now, some other seizures can start in a small region of the brain. And assume this is brain and the red part is the area where the seizure starts, then this may spread as time evolves very slowly, relatively slowly, throughout the brain. So then the symptoms or the signs may start with a very focal neurological deficit that gradually involves more parts of the brain. I will show some videos later on. So this is time, as time continues, this particular seizure may evolve to a secondary generalized seizure, as opposed to, shown in the lower panel now, the primary generalized seizure. So what is epilepsy? Well, epilepsy is a medical condition that is characterized by an increased likelihood of seizures. So it's good to differentiate epilepsy from the seizure. The seizure is what the patient experiences, what you can see oftentimes. And the epilepsy is basically his or her brain condition. So patients with epilepsy have brains that tend to create seizures. And of course, if a patient visits the neurologist for the first time and you think from history taking that he or she has suffered from a seizure, it doesn't mean that he has epilepsy, because it could be a single incidental seizure. But of course, at that moment, an important question is how likely is it that this particular seizure will recur? Because if there's a significant chance that it will recur, then it is by definition epilepsy, because then there's an increased likelihood of seizures. Now, that's not always a trivial process, and there are different ways to figure that out. And one very important measurement tool is the EEG, the electroencephalogram. So what's an EEG? Well, an EEG is essentially a recording of the electrical activity of the brain, and this is possible, fortunately, through the intact skull. So you can place electrodes on the scalp, and when the brain is functioning properly, you will be observing brain rhythms in the frequency range I just told you. And very often the most dominant rhythm, particularly with the eyes closed, is in the alpha range between 8 to 13 hertz. And the source of the EEG is mainly the pyramidal cells in the cortex that are aligned in parallel, and each pyramidal cell essentially functions as a very small current dipole, creating very small extracellular currents. But as there are so many in parallel, the current is typically large enough to induce significantly large voltage drops across the scalp that we can measure. And another important characteristic is that they oscillate, they fluctuate. We will not go into detail why this is the case, which is neither trivial, but the observation is that apparently the pyramidal cells tend to oscillate, creating rhythms that we can record with the EEG. And it's mainly the currents resulting from the synaptic input that are responsible for the EEG. It's not the action potentials, it's the synaptic input, excitatory and postsynaptic inputs to all the pyramidal cells in the cortex that are in part synchronized, resulting in these brain rhythms. Now, an example of two other epochs of a normal EEG. This is eyes closed, eyes open. This is time in seconds. And these are the different recording positions. We'll not go into detail now. And this is an eyes closed and this is an eyes open. And you can already clearly see a huge difference between the two conditions. When you open your eyes, a lot of the rhythms are suppressed. And this is basically an artifact resulting from the eye blink. In fact, you are measuring a different position of the retina that is recorded with the EEG, because there's also a transretinal voltage that is reflected in the EEG when you close your eyes, because your eyes move backward. Now, I just shortly touched upon the EEG, that it basically measures excitatory and inhibitory postsynaptic currents resulting from the postsynaptic potentials. And this is displayed again here. So this is a neuron receiving inputs As you know, many neurons receive both excitatory and inhibitory input. And depending on the balance between those two, the neuron will either generate action potentials or not. And what is also shown here, that in this particular neuron, if there's an inhibitory input, the resting membrane potential may drop a little bit. And when there's excitatory input, it may increase, and depending on the strength of the excitatory input, actually the net excitatory input, the membrane potential may reach the threshold of the voltage-gated sodium channel, and then an action potential is generated. Now this happens throughout the whole cortex, and in part this process takes place in a synchronized way, so many neurons synchronize, but they do differently in different regions of the brain. So if you would record at different positions across the scalp, we would measure different rhythms, different frequencies, different amplitudes. They serve different functions and they create different rhythms. That's the physiological state. If a patient suffers from a seizure, however, you may notice something like this, as for instance is the case in the patient with a generalized seizure. So all the brain areas essentially create the same rhythms. So that is during the seizure. But the interesting observation is that in many patients with epilepsy, we may also find subtle discharges in between the seizures. So they don't have the seizure, but if you record the EEG, now and then you find a short duration of abnormal synchrony. Too short to give clinical signs or symptoms, too short to generate a seizure, but it is a signature of epilepsy. So it's a very specific sign for patients with epilepsy. So you could observe, for instance, an isolated spike wave discharge in a particular patient, but not a whole run. And that is one of the reasons we make EEGs in patients who may suffer from epilepsy. We basically search for the interictal discharges. Now I will show you a few examples of patients recorded in our clinical neurophysiology department that show some of those interictal discharges, and in some patients even some seizure activity is shown. So this is an example of a young patient. This is the EEG with the different recording positions. There are some artifacts here. This is the EKG, and this patient shows a particular seizure, or actually myoclonia rhythmic jerks in response to photic stimulation. So at this moment we use photic stimulation in a particular frequency, and now the frequency will be larger, and if you look carefully then you will see muscle twitches from the arms, and the EEG displays epileptiform discharges. So this is a particular kind of reflex epilepsy where you can induce epileptiform discharges by exposure to stroboscopic light, and the patient will experience jerks. Now, if you would look at a longer recording of this EEG, you may also find some interictal discharges that are not induced by the photic stimulation. So they are really interictal discharges. And all these observations help to make the diagnosis of epilepsy more or less likely. Now, this is definitely epilepsy, and in fact, this is a patient with a juvenile myoclonic epilepsy. This is another patient with very subtle contractions of the thumb and the index finger, and where we thought that the origin might be from the cortex. Actually, it's a particular kind of epilepsy, or maybe even it should be called cortical myoclonia. And if you look carefully, this is the right hand and this is the left motor cortex, then you can find now and then little very subtle discharges just a few milliseconds before the twitch of the hand. And these are the discharges we are looking for as clinical neurophysiologists. Now, you don't have to remember this, of course, or know this in detail as a student, but it illustrates the relevance of the EEG in particular conditions. So these intermittent, short duration muscle jerks find their origin in the cortex and not, for instance, in the spinal cord. Here again, we see this interictal discharge and the response of the patient. Now, this patient also suffered from more severe seizures where this was more continuously. So it's both cortical myoclonia and symptomatic seizures in this patient. Now in closing, another patient we saw at the neurophysiology department that shows an abnormal motor behavior as well. So this again is the EEG, some eye blinks, some EMG. And it's a young patient, a young woman. And if you look carefully, then quite suddenly the patient will show definitely abnormal motor behavior. It starts right now, of arms mainly, and hands, a little bit of the legs, and the accompanying EEG pattern. Now this may suggest a generalized seizure, but this is a pseudo-seizure. So this is a patient who suffers from psychogenic seizures, and that is one of the things that are in the differential diagnosis of seizures, that the seizures have another origin than epilepsy, and those are referred to as psychogenic seizures, which is still a non-trivial problem, how to treat it and how to diagnose it. Very often is associated with epilepsy, so a lot of patients with epilepsy also have psychogenic seizures. There's a lot of research going on in that field, but for now it suffices to say that not everything that moves in an abnormal way is a result of epilepsy. In this case, it's a psychogenic seizure. So in sum, we discussed some aspects of epilepsy and seizures. It's important to know the difference between the two. And very shortly, we touched upon the role of the EEG. There will be other screencasts where that will be discussed a little bit more in detail. But for now, it suffices to say that the EEG is an important part of the diagnostic workup of patients with epilepsy, as it may display interictal discharges that are very specific for epilepsy. Of course, if a patient comes to the physician, we don't only make EEGs. In most cases, we will also do, of course, an MRI scan or a CT scan of the brain, and of course, very carefully history taking and neurological examination. But the EEG is a very important component of the diagnostic strategy in epilepsy. That's the end of this screencast. Thank you very much.